All right, we're going to get started on chapter 8. First section of chapter 8 is the order of an integer mod n. Right? As a motivation, let's start with Forever's theorem. States for every n bigger than 1, and it's an integer, and a in z relatively prime, to n, we have a to the p of n. This is congruent to 1 mod n. So in other words, there is at least one positive integer that is p of n. When you raise a to, it gives you congruent to 1 mod n. However, there are there are some cases, actually many cases, there are some cases where a smaller exponent, let's say h, where h is less than p of n, and the congruence a to the h is congruent to 1 mod n holds. Means for smaller components, actually other than p of n, we do have this congruence becomes congruent to 1 mod. So by the will ordering principle, the will ordering principle, there is a least integer or smallest integer let's say k, such that a to the k is congruent to 1 mod n. And this is the integer we are interested in, and this is the integer which we call the order of actually the integer a mod n. All right? So this leads to the following. We're going to do this one formally. This leads to the following definition of the order of a mod n. All right. So here it is. And mainly, actually, the objectives of this section is mainly to study this concept, all right, and to look at the special case when the order actually of an integer is phi of n, means the smallest value happens to be phi of n, and those kind of numbers we call them primitive roots. Okay. So we're going to get to that, but this is basically what it is. So here's the first definition. Again, let n bigger than 1 and a in z relatively prime. And we're going to see actually it must be a relatively prime for this concept of order to make sense. Okay? So and a in z relatively prime towards n. The order denoted by this symbol, order sub n of A. By the way, the book does not use this notation. It's very, very nice, useful notation. It is used, on other places in group theory, ring theory, and so on. So I'm going to be using this notation to the order of A mod n. It's the way it's given. Is the smallest, which we know actually it does exist because of the will order principle, is the smallest positive integer k such that A to the k is congruent to 1 mod n. To put it in a different way, that is order of A mod n equal k if and only if A to the power k is congruent to 1 mod n, and A to the power of h is not congruent to 1 mod n for all h, for all integer h bigger than 0 and less than k. So it is the smallest among all the powers that you raise A to give you a congruence to 1 is called the order, which is in this case k. All right, let's look at some examples. So in other words, the order of an integer depends on both A and n. Right? For a fixed n, different number, they're going to have different orders. Okay? So here's some examples. At n equals 7, and let's consider the order mod 7 of 2. What is this is equal? Since 7 is a small number, we could do trial and error. Means we could do 2 to the 1. This is, of course, is not congruent to 1 mod 7. Then we take 2 squared, that's equal 4, and this is not congruent to 1 mod 7. 2 to the third, this is equal 8, and yes, 8 is congruent to 1 mod 7. And from the way of course, we've done this, means going the smallest and the larger and so on. This, therefore, the order is this is the smallest exponent. We put 5, and this is equal to 3. Let's consider the order of a 3 mod 7. So what this is equal. In this case, again, 3 to the 1 is not congruent to 1 mod 7, and then 3 squared is 9, still not congruent to 1 mod 7. 3 to the third is 27, and again, subtract 1 from this, not going to be divisible by 7. And go to the next one, it turns out, after you do the whole exponent, that in fact, the 3 to the 6, all right, is congruent to 1 mod 7. So this is the smallest exponent. And remember, 6 is actually phi of 7. So 7 is a prime, and phi of 7 is equal to 6. So in other words, the smallest exponent, it happens to be actually phi of 7, which is guaranteed by Euler's theorem to actually be congruent to 1. So in this case, then the order of 3 in here, the order of 3 mod 7 is going to be equal to 6. So this is kind of the largest. All right. In fact, it's not very hard to make this remark in here, quick one. The order of any integer that's relatively prime to n, this one is less than or equal p of n. For every n bigger than 1 and a and z with greatest common divisor equal to 1. All right, let's look at one other example. And in the district's example, let me see if I want to do it right now. No, probably not. But let me actually put some other remarks beside this one. The first one, we're going to justify that the concept of order only makes sense for integers that are relatively prime to n. All right? So here it is. Order sub mod n of a makes sense, or is defined, if you wish, only for integers a relatively prime to n. Well, let's prove this. The thing is, if the greatest common divisor of a n is bigger than 1, then a to the k is not congruent to 1 mod n for n. For any k. And in particular, of course, we want it for n k. All right? Prove that we can consider the linear congruence ax congruent to 1 mod n. We know that this congruence has a solution if and only if this is we've done back in chapter 4, okay, if and only if the greatest common divisor a n actually divides 1. That is the right hand side of the congruence. But if greatest common divisor of a n is bigger than 1, this implies that this congruence relation does not, this divisibility condition a n is not going to divide. All right. So this means that we have a to the k is not going to equal. Now, but we still have one other thing. All right. Actually, we wanted to say this one for any k bigger than or equal to what? We are interested only in positive, all right, actually exponents. The case now, let's see that what happens if we assume that there is an exponent that actually is congruent. In other words, we haven't done with the cyclade yet. Assume that by contradiction, let's assume that a to the k is congruent to 1 mod n for some k bigger than or equal to 1. This implies that a to the k is equal to ak multiplied by ak minus 1. Sorry, a times. Yes, and this exponent in here is bigger than or equal to 0, of course. And so we have the AK, which is equal to this product, and we know this one is congruent to 1 mod n. That's our assumption up here. And this means, this implies that x equal AK minus 1 is a solution to this congruence AX congruent to 1 mod n. But this is a contradiction because we say that this congruence has no solution. All right? Because this is not satisfied, and probably we could add something in here. This implies that AX congruent to 1 mod n has no solution. In the case, the greatest common divisor of A and the n actually is equal to 0. All right, which means that we cannot have any exponent, any positive exponent of A to make it go to congruent to 1 mod n. All right? All right, so from here on, whenever we talk about the concept of order, if with or without stating the condition that the greatest common divisor with A and n must equal to 1, it must be implicitly understood that it is. All right? So a lot of cases I usually state this, but if I slip and I don't, it means, or in the book the same, it means that it is, when we talk about the order of an integer, means the integer is congruent to n. Okay? All right. Let's move on to another remark. If we have A is congruent to B mod n, then the order mod n of A and B are the same. And again, here is a place where I did not state that the A and the D must be relatively prime to n. So to be understood, if we're talking about order. All right? And this is very simple. Proof of this, A congruent to B mod n. Back in chapter 4, we talk about congruences. It means that, maybe chapter 2 actually. All right, so this one means that A to the k is congruent to B to the k mod n. Actually, for every k bigger than or equal to 0. All right, so let's assume that the order of, let's say, A is equal R, and this implies that A to the R, all right, is congruent to 1 mod n, but also A to the R is congruent to B to the R. mod n. All right? So at least I know that p to the r actually is congruent to 1 mod n. Now we need to show it is the smallest. All right? So to show r is the smallest positive integer such that p to the r is congruent to 1 mod n. Well, let's assume not. Assume that, because it's not enough to just show that, remember that p to the r is congruent to 1 mod n. It doesn't make r is a odd. We need to show it is the smallest. All right, and that's what we're trying to show here. So let's assume that p to the s is congruent to 1 mod s. Mod n for some s less than r. Well, again, because of the same talking about the congruence in the top, here this holds for any. So this implies b to the s is congruent also a to the s. And since b is congruent to 1, b to the s, then a to the s is congruent to 1 mod n. And this is a contradiction if we are assuming that s is less than r. So it means that we actually r is, so this implies r is the order. Let me just try it in simples. So this implies the order of p mod n is equal to r. All right. Let's move on to the fifth theorem, which actually would offer another way of doing this proof. And I will actually point to it. Here's this theorem 8.1. And it reads like, again, let the order of A is equal to K. Then A to the H is congruent to 1 mod n if and only if K is divisible by H. In some sense, it reflects that the K is small, right? The smallest. So if there is, an exponent to which you raise A to, it gives you congruence to 1 on n, then the order, all right, is going to be a divisor of this H. And this is the, so this is an if and only if, all right? So let's just start with assuming A to the H is congruent to 1 mod n. All right? Now we're going to apply the division algorithm to H and actually and K, okay? But to H and K, like this. We're going to write H, because in some sense, A is the bigger one supposedly, right? So we're going to divide it by K. So this is QK plus R, where R bigger than or equal to 0, less than K. Now let's raise A to the H. All right, this is equal A to the Q, K plus R, and I can separate this into two factors, A to the K to the Q, and then A to the R. Now we're just going to take a congruent to A to the K, because the order of A is K is equal to 1, so we have 1 to the Q times A to the R. And 1 to the Q, of course, is equal to 1, and this becomes congruent to A to the R mod N. But remember that we have A to the H is congruent to 1 mod N, that's by assumption. Since A to the H is congruent to 1 mod N, this implies, together with the H is congruent to A R, this becomes mod N. But since A has ordered, the order of A is equal K, and R is less than K, this implies the only way to make bigger than or equal to 0 is only holds, in other words, R cannot be a positive integer. So this implies R is not a positive integer, and this implies it must equal to 0. Right? So there is no positive integer smaller than K where you take A to the R congruent to 1. So that cannot happen. All right. What does this mean? This means that R is equal to 0, and we already have this from here. We have this implies that H is equal to K, and this means K divides H. All right, so this takes care of one direction. The other direction is actually pretty much reversible, means we just need to, the last two steps of this proof that we have. So let's assume that K divides H, and this implies that H equal KQ, you know, because the same Q there, and this implies A to the H is equal A to the KQ, and this is equal A to the K to the Q, and but A to the K is congruent to 1 mod N, and this of course congruent to 1 mod N, and that's exactly the other direction where A to the H is congruent to 1 mod N. All right. As I said, we could prove the previous remark using this. So this is what we have. So this is proof of the remark. So we have A is congruent to B on N implies, and so we want to show that order of A is equal order of. So let's assume that the order of A equal K and order of B equal K prime. So I want to show that A is the same as K prime. So from here we have A to the K is congruent to 1 mod N. And also we have A to the K is congruent to B to the K mod N, because this is properties of congruences. So these two implies that B to the K is congruent to 1 mod N. Now, together with the theorem, since the order of B is equal K prime, so this implies that K prime divides K. And you reverse means you take the this one, all right, gives you B to the K prime is congruent to 1 mod N. And this congruence relation in here, this one also gives you A to the K prime must be congruent to 1 mod N. And now the order, this gives you the relation that K divides K prime. So both of these K prime divides K and K divides K prime implies they are equal. Now remember, these are all positive integers. Less than or equal give you in both cases, and positive integer give you equality. You don't need absolute value. All right. Here's another corollary to also to the theorem. Because we know that A to the phi for any integer relatively prime to n equal 1, congruent to 1, that's Euler's theorem. So then we have A and Z, the relatively prime to n bigger than 1. Then the order A divides phi of n. All right, and also this implies that the order is less than or equal to. And the proof of this is, of course, very simple. We have this on n. This is by Euler's theorem. And the theorem implies order of n must divide, okay, phi of n, because we have an exponent of A to the phi of n congruent to 1 mod n, so the order must divide. All right, and the result of this, of course, we have this inequality. All right. Now, this corollary actually provided us a shortcut for finding orders of some integers. All right. So in other words, it's useful, even though it is very trivial as far as a conclusion of the theorem. All right. Corollary provide a shortcut to finding order of integers. some examples. So let's look at finding the order of of 5 mod 17, for example. Well, without the corollary means we have to raise the 5 to all powers from 1, 2, 3 up to 5, and a smallest integer, the first integer, to give us congruent to 1 mod 17. But in here, I know that since this order must divide p of 17, which is equal to 16. This implies that the possible values of order of 5 mod 17 are 1, the divisors of 16, 1, 2, 4, 8, and 16. So it is much less numbers to actually try. And of course, it's not 1. Check this one. 2, that's at 25, and 25 is not congruent to 1 mod 17. How about 4? Actually, 4, you're going to see that it's not congruent. 8 is not, so it's going to be actually 16 itself. So 5 to the 16. And remember that you could do this one with successive squaring. Okay, so you don't need to raise 5 to the 16. So this one is mod 17. And this makes the order mod 17 of 5 is equal to 60. So the p of 70. All right. Before we state the next theorem, that's theorem 8.2, we need a lemma that you have seen actually in homework problems. Second homework, special case at least of it. So we want to prove this is in general. And that is, if A and B are relatively prime, then A to the n and B to the n are relatively prime for any positive integer n. Okay, so first we need this lemma. A, B equal to 1, then get this common divisor. A to the n, B to the n equal 1 for every n bigger than or equal to. You see in there when we have this one is equal to 1 and you are asked to prove that a squared and b squared are relatively prime. So this is actually true for every n. And the proof is by induction. And what we're going to show, first, we show greatest common divisor of a to the n and b is equal to 1. For n equal 1, of course, the statement is true. This is true by assumption. So let's assume a to the k b equal 1 for some k bigger than or equal to 1. And we're going to consider a to the k plus 1 and b. All right? All right. Now, since a to the k plus and b is equal to 1, then by identity theorem or lemma, since A to the K B equal 1, this implies there exists X, Y, and Z such that A to the Kx plus By is equal to 1. We also have AB equal 1. This implies there exists U and V in Z such that AU plus BB equal 1. Now we're going to multiply these two identities, and then we're going to see that the AK plus 1 is going to appear as in the combination. We're going to multiply so this is the first one is 1 times 1 equals the other one that's equal to 1. All right, so when you apply this, you can see that we're going to get A to the K plus 1. And we're going to get U. All right, and we actually first multiply it and then we'll see what we have. XU here. And then we have plus A to the K BV plus by times A, so this is A B Y U plus B squared Y B, and this is equal to 1. So all we have to do to rearrange this so that we have a multiple of A to the K plus 1, and everything else in here, I want to make it a multiple of B. So this is A to the K B plus AYU plus BYB. This is 1. And this implies that A to the K plus 1 be equal. All right. Now the other, so by mathematical induction, that A to the N be equal 1 for every N bigger than or equal to 1. Now, by symmetry, or even you can do a trick, very cheap trick, is this. We have A to the N, all right, and B. This is the same as B A to the N. All right? So if you call this C, all right, then by the first argument, and this is equal 1, right? This is, we prove this equal to 1 by the first argument. We have B to the N C is equal 1 for every N bigger than or equal to 1, right? So who cares? It is A, B, all the same. And therefore, we have B to the N, A to the N, which is the same as A to the N, B to the N equals 1. Okay. All right, now we come to the next theorem. And this is theorem 8.2. Says that let the order of A equal to K, then A to the I congruent to A to the J mod n, where I and J's are bigger than 0. They're bigger than, or we could take or equal to 0 even, yeah. If and only if the exponents are congruent to each other mod k. All right? So here's the proof. Now let's go with this direction. Let's assume that A to the I is congruent to A to the J mod n. Now, also without loss of generality, you can assume that I is bigger than or equal to 0. Now, since A and N is equal to 1, then A to the J and N also is equal to 1. So these are relatively prime. Then we can divide this congruence. We can divide the congruence relation, which is A to the I congruent to A to the J mod n, by A to the J, the smaller exponent there. All right? And this would imply that AI minus J, which is a positive exponent, and then the other side is cancel out, mod n. Remember that if we have a coefficient, if we have a number that is, relatively prime to n, we can divide by n, by that number. All right. So we have A to the I minus J is congruent to 1. Now, by the previous theorem, this implies that the order of A is divisible by this I minus J. Okay. By theorem 8.1, we have K, which is the order, divides I minus J. And this is equivalent to saying that I is congruent to J mod. All right, we're going to go the other way around. Assuming the I and the J are congruent. Go this way, in the proof. Assume that I is congruent to J mod K. And we wanted to show A to the I is congruent to A to the J mod n. All right. Now, once again, let's see what does this assumption means. So I congruent to J mod K means that K is divisible by I minus J. And this implies I minus J is equal to QK for some integer q. And this implies I equals j plus the q, okay? And let's take a to the I is equal a to the j plus qk. And this is equal a to the j multiplied by a to the k to the q. Now let's do a congruence here. A to the j. Now a to the k, that's 1 to the q, and this is congruent to a to the j mod n. Right? Because because a to the k is congruent to 1 mod n. Okay? And that's actually the second part of this. All right. Corollary to this, all the exponents of a, they are going to be incongruent mod, actually mod n. All right? So we write this corollary precisely. If the order mod n of a is equal to k, then a squared up to a k, and this is equal congruent to 1 mod n. All right? Incongruent, they are not congruent to each other. Incongruent mod n. Or another way of saying this, we call them incongruent in pairs. None of them congruent to any of the others. All right. So the proof of this, we're going to do this by contradiction. So let's assume that a to the I is congruent to a to the j for some mod n, for some I and j. This time is between 1 and k. It's not arbitrary. So this must be up to k. All right. Then by the theorem, this implies, because these are congruent to mod n, that I is congruent to j mod k. And this implies that k divides I minus j. And let's assume in here that we're going to assume, without of course this of generality, that the I is actually bigger than j. All right, so when I say I minus j, we have that as a positive number. All right, so then we have the k is less than, and this in itself implies that the k is going to be smaller than or equal to I minus j. All right. On the other hand, we have since I and j, and let me actually put this one like this: I bigger than j, and this one is less than or equal to k, and bigger than or equal to 1. So this implies the difference between these, I minus j, is going to be, and they are not equal to each other, so this one is going to be strictly less than k. So in order for both of these to actually hold, k is less than or equal I minus j and I minus j, only way this could happen is implies that I minus j must equal to 0, and then we have R. Okay? So in other words, these exponents, so in other words, I should say so. My contradiction assumed that these, for some, and let me say these are not equal to each other here. Okay? Or for some I does not equal to j between 1 and k. All right? All right. Now, next here, so in other words, in here, sort of, there is this relationship between order of an A and then the powers. The question might be asked, is there any relationship between the order of A and the order of powers of A? Since these are kind of related in some sense, then the question is, suppose I want to find the order of A to some power. Is there a way, can we express this? Can we express this in terms of order of A? And the answer, of course, is yes. And this is theorem 8.3. And this one there says that this, if the order of A is equal to K, then the order of any power of A to the H is equal. K is the order of A divided by the greatest common divisor of H and K. All right? Here's the proof. First of all, we have, let's assume that the greatest common divisor of H and K is equal to D. Okay, so we're going to get D equal greatest common divisor H and K, and this implies that D divides H and D divides K, and D divides H means that H is equal D H1 and K is equal D K1. Now let's look at kind of what we are supposed to show there. This one to the power of the right hand side is congruent to 1 mod n. All right, at least to show that it's gonna satisfy the congruence. Okay, so we're gonna take A to the H, and we're gonna raise this to the power of K over the greatest common divisor, which is D. All right, and now we're gonna substitute for the D by what's equal to, so we're going to do some manipulation in here, and let me actually take this one, A to the H, and K over D, and from here we have the K over D is equal K1. I want to put here a K1. All right, and let's also substitute for the H by, let me see what I want to do in here. So this one is, I want to bring in the K somehow in here. So I want to bring in so this becomes A to the DH1 to the K1, and this is equal to A to the power dk1 and h1 outside. But a to the power kd1, this is equal to k, h1, and now we're going to do congruence. A to the k is congruent to 1 mod n. And so we have, yes, it is congruent to 1 mod n. So this one implies this is 1 mod n. So the first thing we have is this exponent, all right, a to the k over d, which is what this side is, okay, is congruent to 1. Now let's see, what does this imply? This implies that, again, this relation now we have since order A is equal to K, all right, and we have and A to this exponent. Let me see which exponent I want it to be in here, actually. Before I do this, okay. We do one other thing in here, and then we'll use that. All right. So let's assume let the order of a to the h, okay, mod, and let me call this as r. All right. And now we have since a to the h to the power k, actually k over d, we write it like this, and then I will write it as k1, all right? This k1 is congruent to 1 mod n. That's what we have shown here, right? By theorem 8.2, which is the previous theorem, or 8.1, in fact, for 8.1, the R must divide this exponent, HK1. All right, so we have this. Sorry, just K1. Okay, so the order of A to the H. So the R, the order divides whatever exponent make this is equal to 1. I would like to find another actual relation go the other way around, and then we conclude that R and the K1 is going to be equal to each other. And to do this, going to go like this. Now we have, once again, the order of A is equal to K. So this implies A to the power of, and what is K is equal to? Remember that we have K is equal to, let me see it here. Actually, two things. We have this. This implies this one, mod n, and we have A to the H to the R, also is equivalent to 1 mod n. All right? But since the order of A is equal to K, and both of these, and this one is of course A, H, this is equivalent to 1 mod n, then this implies that K must divide HR. And let's now substitute for HR. Let me put the relationship. Remember that H is equal D H1R. And also we have K is equal DK1. All right. Now, let's look at all of this. All right. So in here. So I want to put DK1 divide for the K, and then I'm going to substitute for the HR by D H1R. First of all, the D cancel out, and the H1 and K1, these are relatively prime because these are actually the one which we obtained from this. We have D divides K and D divides H. And then we wrote that this one is actually, it says that K is equal D K1 and H equals D H1. And with this, it makes that the greatest common divisor of K1 and H1 is equal to 1. All right, now since K1 divides H1 times R, and these are relatively prime, then by Euclid's lemma, then the K1 must divide R. All right, now we have this relation and this relation, this divisibility relation. Both of these implies, so these two implies that R must equal K1. And remember what this K1 is equal to. Is K over the greatest common divisor of H and K. And this actually finishes the proof. All right, let's see how much we have. Let me do a couple of corollaries, and I'm going to stop actually because it looks like and maybe give some examples. All right, this is going to take a little more time, so I will just give some corollaries to this. The first corollary, which is very simple, corollary. Again, let's assume that the order of A is equal to K. Then the order of powers of A is equal to K if and only if H and K are relatively prime. All right, this is very simple. Call that we have by the theorem the order of A to the H is equal to K divided by the greatest common divisor of H and K. So if this is going to equal K, if and only if the denominator equal to 1. And this is it. That's what really this corollary is saying. This one is equal to K, all right? And this is equal to K because we have a fraction in here, equal to K if and only if the denominator of it is equal to 1. And this one means they are relatively prime. All right, let's look at another more important corollary. And since we have part of it is we need the order. So this is corollary 2. We're going to be referring back to this corollary later on, so just remember. All right, actually in this next lecture, all right? All right, then there are exactly P of K numbers among the integers a squared up to a E of n. K, a to the k. Has order k mod n. Of course, the last one is not, because it's going to be equal to 1 mod n. Unless a is also 1. All right? In particular, if the order of A is equal to P of n, Euler's phi, then there are P of n integers among a squared up to a or P of n has order P of n. Now, once the k is equal to this, that's really what this statement is saying. Then there are P of n of these numbers that has order P of n for mod n. All right, this part is actually another corollary stated later on. So since it is natural places here, that's what it is. Once I show this, then this will be a special case. All right, let's prove the first part. All right. Now let's look at the definition of what is. Let me actually take this out in here, because this is really a very, very special case. The proof. By the definition of P of k as the number of integers among one, 2, up to k that are relatively prime to k. So this is the definition of the phi of k. Now, remember that the order by the previous actually corollary, the order of A to the H. All right? This one is equal K if and only if H, greatest common divisor, H and K is equal to 1. So in other words, how many of these are there? So there's going to be phi of K. This implies there are phi of K values of H such that H, K is equal to 1, and hence A to the H is congruent to 1, actually A to the H to the K. Or maybe just say what the statement, and hence the order of A to the H is equal. All right? Very simple proof, actually, as you can see. All right, let's look at some example to illustrate all of this. Okay? And including the last statement in here. So let's just see how the theorem actually works. Here's some examples. Let's take, we have the order mod 13 over 3 is equal to 3. And you can check this since 3 to the 1 is not congruent to 1 mod 13. 3 squared is 9. And this is not congruent to 1 mod 13. And 3 to the third is equal to 27. And this is yes congruent to 1 mod 13 because the reference is 26. So we have this. Now, by the theorem, if we want to look at the order of, let's say, 3 squared. All right, 3 squared, it's going to be, according to the theorem, it's going to be the order over 3 divided by the greatest common divisor of the exponent 2 and 13. Okay? H and K. The denominator is 1 and the order of this is 3, so this is equal to. So the order of 9 is actually is equal to 3. All right? Let's look at another one. Order of, let me see if I want to. Yeah, let's take a look at order of 2. This happens to be, okay, and again, we could see this one from Euler's theorem. They had 2 to the 12 is congruent to 13 mod 1. But it is the smallest one. It turns out that this one is a 12. And so this is phi of 13. All right? And now if you want to take the order 2 to the 4th, for example, I think this is what I have in here, or to the 3rd. Is equal to 12 divided by the greatest common divisor of the 3 and 30. right? And this is going to be also equal to sorry, 3 and 12. 12. This one is a 3, and the is the exponent with the order. Sorry, 12. Say something is wrong, and this is equal to 12 over 3. I'm sorry, this one's supposed to be the order of 3, 3, 3, 3. So, yeah, the exponent and the order of the element, which is 3. Fortunately, this is a correct answer, but the incorrect, justification. All right, let's look at one other example to illustrate the corollary, the second corollary. So in the second corollary, we have, let's look at the order of the 3 mod 7. This happens to be actually 6, which is phi of 7. Okay, which you can check. Now let's look at these powers, all right? 3, 3 squared, 3 to the 3rd, and so on up to 3 to the 6th. And says that among the integers in the set, the above set, there are phi of 6 that has order 6 mod that's 7. That's what the corollary said. Now it turns out that when you do the calculation of this, the dual, and now this one in here, phi of 6, to start with, this is phi, and phi of 6 is actually equal phi of 7. Phi of 7, sorry. Or phi of 7 we know it's equal to 6, and phi of 6 is equal to 2. All right, the only two primes relatively prime to 6 between 1 and 6 is 1 and 5. All right? Now, which are the integers that are among these? They have order 6. So the only integer they have order 6. And have order 6 are, of course, the 3, the first one, and 3 to the 5th. And the 3 to the 5th, it happens to be congruent to 5 mod 7. So only 2, and this does agree, of course, but the counting number is supposed to be phi of 7. All right? But you can check the other ones. They're going to have order less than 6. All right? All right. This section is not finished yet. There are a few more things I need to finish up on this. It's going to be a little short, but I want to stop right here.